Hello everyone, welcome to our channel. Today we're gonna solve Cascade Refrigerator systems. We have one solution to solve it. Our solution has a two-stage Cascade refrigerations from here. A two-stage Cascade refrigeration system operating between the pressure limits of 0.8 and 0.14 megapascal. Each stage operates on an ideal vapor compression refrigeration cycle with refrigerant 134A as the working fluid. Heat rejection from the lower cycle to upper cycle takes place in an adiabatic counterflow heat exchanger where both streams enter at about 0.32 megapascal. This is 32 megapascal lines. In practice, the working fluid of the lower cycle is at a higher pressure and temperature in the heat exchanger for effective heat transfer. If the mass flow rate of the refrigeration through the upper cycle is 0.05 kilogram per second. First, we're gonna determine the mass flow rate of the refrigeration through the lower cycle. This is our lower cycle. We know that and we assume that this is the steady operation conditions, and we neglect change in the kinetic energy and potential energy, and we know that the heat exchanger is adiabatic. Mass flow rate of the refrigerations through the lower cycle. We know that the power output equals the power input, and we can use this formulation. This means that a point between 5 and 8 and point between 2 and 3 equals power input or output. This question, we're gonna use table of R124A to find enthalpies of this system. And we know that the mass flow rate for the first one, 0.05 kilogram per second. And we have to check the table for the finds H5 and H8. These are and our aim is to find mass flow rate, the point B, and we can find enthalpies point 2 and 3 from the same table. All of these calculations we can find mass flow rate point B equals 0.039 kilogram per second. This is our first step. Then second step is rate of heat removal by a cascade cycle. This is equals to QL, and in the system QL equals mass flow rate point B times H1 minus H4. Again, we use the same table to find the H1, and H4 can be calculated for the H3. and the QL is equal to 7.18 kilowatts. And the power input can be calculated by the compression 1 to 2. We know that working equals the compressor 1 plus compressor 2, and compressor 1 has a mass flow rate of MA, then H6 minus H5 plus compressor 2 has a mass flow rate of MB, and this is between the H2 and H1. We can find all of the enthalpies from the table. We know that MA 0.05 kilogram per second, and we know H6 2. And working equals 1.61 kilowatts. Our last step is finding COP for the refrigerator system. COP for the refrigerator system is equals to QL over initial working. We find QL and work net in. And it can be calculated from these data. This is equals 4.46. Thank you for listening to us.